Hey guys, I have your notes here for section 11.3, day 3. So what we're going to do is we're going to, again, look at polar curves, look at how they're graphed, and then do some cool stuff with them, like, hey, let's make a tangent line on one of them, or hey, let's find the area inside one of them. So we're going to get started with the example on the front. We're going to write an equation of a tangent line. So we want the tangent line at the point where theta is pi over 6. So we need the slope there. And remember, slope of a line, of a tangent line, looks like this. We need dy dx. And then to make our tangent line, we not only need dy dx, but we need a point. We need rectangular coordinates for a point. And we're starting with a polar equation. So in order to get dy dx, I've got to convert this to rectangular. The conversion for rectangular, the formula, of course, is x equals r cosine theta, y equals r sine theta. And to get dy dx, you're going to need dy d theta over dx d theta, so that your d thetas cancel out. So here I go. Dy d theta is going to be on the top. So I'm going to go, let's see, 1 d2 plus 2 d1. So when I do d1, I've got the coefficient out in the front. I did derivative on sine of 3 pi, and then I chain ruled it. Don't forget to multiply by the 3. On the bottom is dx d theta. So again, 1 d2 plus 2 d1. You can simplify that if you want, but since I think it'd be just as much work to simplify it as it would be to just go ahead and sub in pi over 6 at this point. So I did. I wanted to go ahead and sub in pi over 6. However, I tend to have a hard time keeping track of a bunch of things in my head at one time. So I knew if I tried to sub in pi over 6, multiply by 3, find the sign of all that, I would get lost. At some point, I would mess up somewhere. I just knew I would. So I subbed in and multiplied by 3 when I needed to, or subbed in directly when I needed to. And then I did my trig. Then I did my sine of pi over 2 and my cosine of pi over 6 and all that good stuff. And I got dy dx to be negative radical 3. That's the slope of my tangent line. Now, I have the slope. Now I need a point. I need xy coordinates. So to get xy coordinates, I'm just going to go back up here to my x and y equations. I sub in pi over 6 into my x equation, and I get my x coordinate. Sub into my y, and I get my y coordinate, and there you go. There's the equation of my tangent line. These were positive. They're in quadrant 1. My slope did turn out to be a negative. We knew it would. There you go. Next task is let's do the area inside a polar curve. So you know how when we started doing area under a curve in Calc 1, I had you divide it into rectangles. Okay, let's do 4 rectangles, not good enough. Let's do 10 rectangles, not good enough. Let's do an infinite number of rectangles. Okay, so what we did was we took remember along the x-axis, that was our base. So when you divided it into 4 rectangles, your base might have been, that length. And then, oh, not good enough. Let's divide it into 10 rectangles. Okay, well now my base becomes smaller because you've got that separated into 10 portions. What happens when you do an infinite number of rectangles? All of a sudden that base along your x-axis becomes infinitely thin. And I always called that measurement delta x or dx. dx represents that super, super thin base of your rectangle. And then your height of your rectangle was your function over and over and over again. And then we put that in an integral, and an integral does all of the areas and adding automatically. All right, same concept, sort of, but this time with polar curves. So think circles here for a minute. Hold up, time out. I wanted to show you something and I forgot. Go back to here. This is the curve that we found the tangent line to, and this whole curve is completed from theta between 0 and pi. Okay, so I want to show you something super cool. Right here. So that was our equation, that was our x value, that was our y value. I can look at different values of theta, and you can see that from 0 to pi, I am looking at increments of pi over 12. 1 pi over 12, 2 pi over 12, which is pi over 6, 3 pi over 12, 4, and so on, right? Notice when r is the greatest. Remember, r is the distance from the origin to the function. When is r the greatest? Here, I want to talk about this in a minute, and here. So, r is the greatest when my angle is pi, let's see, 1 pi over 12, 2 pi over 6. This point right here, r equals 2, and the radius, the angle of rotation is pi over 6. So these coordinates are 2 comma pi over 6, and this is where our tangent line was. And we wrote it with rectangular coordinates. Okay, so positive r, angle of rotation. Here's what's funny. If you watch this graph being formed, it goes like this. Then it goes like this. And then it goes like this. And it does all of that by the time theta hits pi. Why are these r values negative? Keep in mind, theta has to start at 0 and it can only go to 180 or pi. So we've got theta, this is 90 degrees, pi over 2, this is 180. Why are these negative? Because if theta is restricted from 0 to 180, how are you going to get a graph down here? Because you can't use a radius, comma, angle between 180 and 270. Your angle has to stay between 0 and 180. So what's going to happen is you're going to go from here, that's pi over 6, this was pi over 3, or 60 degrees, and then we jump down here. So what's happening is now my radius has to be a negative value so that my angle of rotation can still be acute. And then the angle gets greater than 90. So negative r value to here, negative r value to here, negative r value, and you see that I'm sweeping an angle measurement greater than 90 degrees to here, and then this would be at, I think this would be at 2 pi over 3. And now My radius jumps positive again because now these are, I can sweep an angle of an obtuse measurement between 90 and 180. Gosh, I hope that made sense. If it made sense, I think that you're going to think that's pretty cool. I just hope I made it make sense. Okay, anyway, back to area. This is what I was getting ready to do. Here we go, back to area. So in geometry, you learned, of course, the formula for area of a circle. Easy. What if you don't want the area of the entire circle? So this gets you the area of the entire circle. What if you don't want the area of the entire circle? What if you only want the area of one sector? Now, a sector is just the formal name for like a piece of pie or a piece of pizza. What if this is the only area you want? You don't want all this. Well, this is what you learned in geometry. Here's how you go about it. Calculate the area of the whole circle. And then say, but I don't want the whole circle. I just want a percentage of the circle. So you take the angle that you want out of your sector and say, that's what I want out of a total of 360 degrees. So you know that this fraction right here, that's going to represent a decimal, and that's going to shrink the area that you had originally found for the entire circle. Except we're in calculus, so we have to use radians. So instead of your angle out of one revolution of 360, now you have to think of your angle one revolution of 2 pi. Well, now this is kind of cool because you've got pi r squared times this fraction. Now your pi's, can cancel. And we're left with a 1/2 and an r squared and a theta. So in radian measure, this is how you get the area of a sector or a piece of pizza, a pie piece. Except now, in order to find the area of a polar graph, I could say, take this polar graph and cut it into 4 pieces of pizza. Take the area of all 4 of those pieces of pizza and add them together. And eventually you've realized, that's not a good estimate. How about we do 10 pieces? How about we cut it into 10 pieces? Can you see how each time we cut it, our angle is going to get smaller each and every time? Okay? 10 pieces, not good enough. Let's think about an infinite number of pieces of pizza. And I call them little slivers, like this little bitty sliver of a piece of pie. Infinite number of those. Well, how thick are they going to be? What's that angle measure going to be? It's going to be so tiny, so thin, we're going to call it d theta. Like we called the base of our rectangles dx, we're going to call these d theta. So now, I've got the 1/2, I've got the r squared, this is that angle, but when I put this in an integral, it does this angle and this r length over and over and over and over again, and adds all of those areas together. So, new formula, area inside a polar curve. It's like a bunch of tiny, thin pieces of pizza with areas added over and over again. So on the back, you've got a polar equation. Here it is. It gives you the picture of the graph, which is all fine and good. But normally you're going to have the equation. I would graph it on my own, on my graphing calculator, to see what it looks like. Also, you're going to need to know how long it takes to make one complete graph. So graph it on your graphing calculator. I would totally guess at first, guess that it's going to take 2 pi, and then you can tell if that's too long or not enough, and you can adjust that accordingly. But turns out this was good. This got me one complete graph. So I'm going to go from 0 to 2 pi, 1/2 r squared d theta. And then if you're good with parentheses, you could just type it in like this into your graphing calculator, or you could simplify it a little bit. So I know that the 2 is going to be squared, and so is this binomial. So when the 2 is squared, it's 4. 4 times 1/2, I just put it out in the front to get rid of it, and that made my integral that I type in my calculator much cleaner. My answer that I got was irrational. And I thought, you know what? I think like 18, wonder if that's divisible by pi. So I tried it. Sure enough, the answer turns out to be really, really clean. This just had the pi buried in it. So this is okay. You know, this is an acceptable answer. Round it to 3 places, but this is better. All right, guys, have fun with this.